This is my video lab report for lab number 5, choose your own adventure. So I decided to do free fall with initial positive velocity. So a little table of contents. So we're gonna have the objectives and then the concepts that we're gonna use in this lab. Then the observed motion by tracker, the predicted motion with glow scripts, and the coding for glow script. Then we're gonna compare the two, have some observations, and then finally we're gonna relate that back to energy. So the objectives of the lab is to apply Newton's second law to a real-world scenario, to measure the effects of drag on free fall versus simulation with just gravity and no drag on free fall, and then observe changes in the components of energy during free fall. Some of the concepts we're going to be using here, so we have Newton's second law, which is force equals mass times acceleration. We have the position update formula, the velocity update formula. Then we have the force of gravity, which is negative mg, g being 9.8 meters per second squared, m being the mass of the ball. Then you have the gravitational potential energy, which is mgh, mg being the same and h being the height of the ball. And then we have the kinetic energy, which is 1/2 mv squared, v being the velocity of the ball. So the observed motion of the tracker, as you can see, I throw the ball up with the initial positive velocity in the y-axis, and then it comes down due to the acceleration of gravity due to the Earth. So the velocity, all right, let's start with the position first. So the position, it goes up and then it stops, the velocity equals 0, and then it starts coming down towards the Earth, and it actually goes into the negative y direction because the origin is at the place where it started. So it actually goes down below the place where I threw it, and then it hits the ground. The velocity, as you can see, it starts positive when it's going up, it slows down, it hits 0 when it turns around, and then it goes all the way back down, and it goes into negative velocity as it's falling back down towards the Earth. So here we have the predictive motion that we did using the code and glow script. So as you can see, it's pretty much the exact same thing, except that there's no drag force incorporated into it. So the position versus time, as you can see, it goes up and then it comes back down with the gravitational force acting on it. And then the velocity versus time is a consistent downward slope, and that slope is negative 9.8 meters per second squared, which is equal to the acceleration, which is consistent throughout the entire time we're present. And then here we have some of the code. So the initial position of the ball is at the origin, so 0, 0, 0. The initial velocity of the ball is 0, 2.980, because I throw the ball with the initial velocity of 2.98 meters per second in the positive y direction. We have g, which is the magnitude of the acceleration due to gravity near the Earth, and that's 9.8. Then we have in the while section, we have the net force, which is equal to the gravitational force, which is the negative mass of the ball times g times j hat, and j hat is the unit vector in the y direction. And then we have the velocity update formula and the position update formula for the ball. So here are the comparison of the tracker and the glow script code, and that's for position versus time and velocity versus time. So as you can see, for glow script, it ends up with a much lower position versus tracker, and it also has a much greater magnitude of velocity versus the tracker. And this is because with the glow script, the only force acting with the ball is the gravitational force, while with tracker, drag is acting against the ball too. So because drag is acting against the motion of the ball, the force is acting against the motion, it reduces velocity and reduces the speed that the ball is going at. So that's why we see that it has a lesser magnitude of velocity compared to the glow script code. So some observations that we find. So the real life tracker shows an accurate effect of gravity and drag on the ball, not just gravity. And the glow script simulation shows a close assumption on the motion of the ball, but does not incorporate drag. So it's not actually an accurate assumption of the ball. And then also for time is less than 1.1 seconds, the force of gravity is greater than the drag force, so the ball continues to accelerate in the negative direction. So let's say the force of gravity was equal to the drag force, then it would be in equilibrium and the velocity would be constant. If the force of drag was greater than the force of gravity, then the ball would actually be accelerating upwards, but since the force of gravity is greater than the force of drag, and the ball continues to accelerate downwards. So finally, we're going to talk about energy. So throughout the entire process, there is a conservation of energy, which means that the total energy stays constant throughout. So the initial energy and the final energy are the exact same. But then we have gravitational potential energy, which is at its maximum at the highest point, where velocity is equal to 0, and this is because the equation for gravitational potential energy is mass times gravitational constant times height, and when the height is at its max, then the gravitational potential energy will also be at its max. And we have the kinetic energy, which is at its maximum right before the ball hits the ground, because the velocity is at its maximum and the height is approximately 0. So the formula for kinetic energy is 1/2 mv squared, v being velocity. So because mass and 1/2 are constant, then the velocity, whenever it's at its highest, that is when the potential energy or the kinetic energy will be at its highest.